All right, today we're going to be starting a new topic. We're looking at the position function, which is called x of t normally. And if you do the derivative of the position function, you get the velocity function. And if you do the derivative of the velocity function, you get the acceleration function. So that's what happens each time you do a derivative. You can see the arrow is telling you. And if we wanted to go backwards, we had the acceleration function. If we were to do the integral, that would give you the velocity. And if we had the velocity and we did the integral, it would give us the position function. Of course, each time you did the integral, you would get that plus c. So you'd have to find a way to solve the plus c. And we're not actually doing that today. So today, all we're going to do is they're going to give us the position function. We have to do the derivative to get the velocity. And they're going to ask us for the velocity at a certain time. So we'll plug that time in. Another thing we're going to do today is they're going to give us the velocity function, and then they're going to ask us to find the acceleration at some time t. So we just do the derivative, and then we plug in that time into our function. So we'll have a look at how you can do that with your calculator as well. The way the position function works is you plug in your t value, and then it tells you the position that you are at that time. The way the velocity function works is you plug in the t value, you plug in the time, and it tells you the velocity at that time. The units are always an amount per time, so it'd be like miles per hour or something like that. It could be feet per second. The way the acceleration function works is, again, you plug in the t for the time, and then it tells you your acceleration at that time. One example could be miles per hour squared, or feet per second squared, or something like that. All right, let's have a look at our first example. Okay, for our first example, it says find the velocity of the particle at time t equals 3 minutes if x of t is equal to 4t to the third meters. So they want us to find the velocity when they give you the position function. So we're starting with the position function. We need to do one derivative, and that'll give us the velocity function. So we're not doing acceleration right now. So the derivative of the position function is going to give us the velocity function. And then we're going to need to evaluate it when the time is equal to 3 minutes. So we'll plug in our 3. So here's our x of t. We do the derivative. The 3 comes down and the new power is 2. So that gives us a 12t squared. So that's x prime of t, but we want x prime of 3. So we need to plug in the 3. You plug in the 3, you're going to get 12 times 9, which is 108. Now, the units of the position function was meters. So when we do the derivative, we're going to get 1 unit of time on the bottom. And the time used in this question was minutes. So we're going to put a minute on the bottom. So our units are going to be meters per minute. So remember, this is the derivative of the position function. But again, that's the same thing as the velocity. So this is v of 3. We're getting 108 meters per minute. Now, how would you plug that in your graphing calculator? Now, on your graphing calculator, you could type this in on y1 of x. But this is a pretty easy function, so I'm just going to type it on the home screen. I want to do the derivative of that function. So the derivative of 4t to the third. And I'm doing the derivative with respect to t, so I'm going to do comma t. And then I want to evaluate it when t is 3. So I'll push the evaluate button, and then t is 3. You can see we're getting 108, so we get the same answer. Of course, it doesn't give you the units. But remember, every time we do the derivative of a function, it's going to have the same units, but it's going to have 1 extra unit of time on the bottom. So instead of meters, we're getting meters per minute. Now, before we go to our next example, I do want to point out one thing. If they gave you the position function and ask you to find the acceleration function, and then maybe plug in a 3, how would you do that with your calculator? So let me just show you real quick. There's only one extra step. Because I want to do the second derivative and not just the first derivative, I'm going to do comma 2 at the end. When I do the comma 2, what it's doing is doing one more derivative of this. This is already the first derivative. If I do one more derivative, I'm going to get 24t. And so that would be x double prime. And again, that's the same thing as the acceleration. So we can say that's the same thing as a of t. And again, we want to plug in our 3. So if we plug in our 3, if we do it by hand, we're going to get 24 times 3. And of course, that's 72. And if you look at the graphing calculator had the same thing. It has 72. So we're just trying to show you like a what if, because in this example, we didn't actually have to do that. All right, let's look at our next example. All right, this example is almost exactly the same thing. Here it says find the acceleration when they give you the velocity. So again, we're just doing one derivative. We have the velocity. We need the acceleration. So we're just going to do one derivative. So we're starting with t to the third. We do one derivative, and that's going to give us 3t squared. So that's v prime of t, which is again the same thing as the acceleration. So we could also call this a of t if we wanted to. And if we wanted to give it one more name, we could also call it x double prime of t, because it's the second derivative of the position function. But we need to plug in our 5. So if we plug in our 5, we're going to get 3 times 5 squared. So that's 3 times 25. And so we get 75 for our final answer. You'll notice the units on velocity were feet per second. So after doing a derivative, we're going to get one more unit of time on the bottom. So the units for the acceleration are feet per second squared. Now let's go ahead and plug this in our graphing calculator and see what we get. Okay, again, we want to go ahead and do the derivative of t to the third. You'll notice I put comma t because we're doing the derivative with respect to t, which is time. But then we want to evaluate it when t is 5. So I'm going to push the evaluate button, and then I want to push t equals 5. All right, we'll push enter. And yes, we are getting 75 for our answer. Of course, the calculator doesn't give you units, so you always have to remember if you do one derivative, the units will get one additional unit of time on the bottom. So instead of seconds, it's now seconds squared. You can see they're showing you one other way you could type it in your calculator if you wanted to. You could type the function into y1 of x, and it doesn't matter if it's x to the third or t to the third, you get the same thing. And then this is how you do the derivative, and then this is how you evaluate it when x is 5. Now if you use a t to the third in y1 of x, then you just need to put comma t right here. But you're still going to have to do y1 of x. So even if you put it as t to the third, this still needs to be y1 of x. So that's a little bit tricky. But again, if you look at my example, it was such an easy function, t to the third. So I just typed it in on the home screen. I didn't see a need to go to y1 and type it in over there. All right, let's go ahead and look at our last example. All right, for our last example, they want us to find the acceleration, and they're giving us the velocity, but they're giving it to us as a graph. So we're not going to easily be able to just do the derivative quickly. Remember, the derivative is the same thing as the slope. So if I want to do the derivative of the v function, that's the same thing as the slope of the v function. And if you look over here, I wrote down the slope for each line segment. The first line segment has a slope of 3/2. The second line segment has a slope of 0. And then the last line segment has a slope of -1. So because this is the slope of v, these are the slopes of v, that means that they're the derivative of v, or you could also say that's the acceleration. So again, they're asking us to find the acceleration, and this is basically going to be the acceleration for any point that lands on each of those line segments. So for example, when t is equal to 4, that would be this point right here, and we're getting a slope of -1. So the acceleration would be -1 at that time when t is equal to 4. Now I do have to say that most examples will give you units. For this one, we're kind of ignoring the units. But again, for the first part, when your time is equal to 4, your acceleration was equal to -1. And again, any point on this little line segment over here is going to have an acceleration of -1 at that time. The only exception would be the endpoints. The derivative does not exist at this endpoint. And then we're going to look at this endpoint as well. You can see there's kind of a sharp corner there. So there's not going to be a derivative there. We'll talk about that more in a second. And again, they want us to find the acceleration when the t is 2, when their time is 2. And that's a sharp corner. When t is 2, you have the sharp corner here. So we already know when there's a sharp corner, the derivative is not going to exist. You can see we have a rule right here for a derivative. The derivative at any point is going to be the limit as x goes to c of f of x minus f of c, all divided by x minus c. So we're going to apply that rule to our velocity function. And because it's a limit, the limit has to exist from both sides. So we'll check the limit from the left. We already know it's 3/2. And we're also going to check the limit from the right. Again, we know that that's 0. And again, in order for a limit to exist, you got to get the same number from both sides. So here we're saying, well, those are not equal. The limit from the left is 3/2. That's kind of like the slope from the left. And the limit from the right is 0. That's kind of like the slope from the right side as x goes to 2. So what this means is this means that the derivative does not exist. So v prime of 2 does not exist. You could also say that the acceleration at time t equals 2 does not exist. These do not exist, and it's okay just to write D and E. The AP grader will know exactly what that means. It means does not exist. If you wanted to put a really good explanation, just look at the bottom down here. The limit from the left does not equal the limit from the right. And that's the reason why. That when t is 2, the acceleration does not exist. Remember, when t was 4, we were fine. The slope was -1, so that meant the acceleration was -1 at that time. And that's pretty much it. So now we can go ahead and just try some of these examples from our homework.